Hello, we are starting with the first chapter of electrical machines, that is three-phase induction motor is our first chapter, and today we will discuss the construction of the three-phase induction motor and have some introduction with it. Three-phase induction motors are very simple in construction because the supply is connected to stator windings only, which is stationary, and the rotor is not connected to any supply, so construction becomes very simple and rugged. The other advantage of these motors are that they are cheap in cost, they having very high efficiency, reasonably good power factor, and they are self-starting. No starting method is to be provided, and these require low maintenance owing to its simple construction. So that's why these motors are most commonly used in industrial as well as agriculture sector. These motors are of two types: squirrel cage induction motor and phase wound or slip ring induction motor. These types are based on the type of the rotor used in the motor. This diagram shows the motor with squirrel cage rotor. So this is squirrel cage induction motor. The main parts of the motor are shown in this diagram. It is after dismantling the motor. This is the stationary part called stator. It is fixed to the foundation with the help of bolts through feet, and this eye is for lifting the motor for installation and repairing purposes. And here is the terminal block where connections are made with the external supply to the motor windings, and inside it is the core windings, etc. And this part is rotor. It's mounted on the shaft. It rotates, and bearings are provided at both ends of the shaft, which are supported by end rings here and this end ring here, and these are two end rings, and then cooling fan and fan cover is there. So these are the major parts of the motor. The main parts of motor are stator and rotor. Stator have further three parts: stator frame is outer body, or outer frame, it is also called outer frame; stator core, this iron core; and stator windings. In the slots windings are placed. And rotors are of two types: squirrel cage rotor and phase wound rotor. This diagram of this rotor is shown here. Here are slip rings, so phase wound rotor is also called slip ring type rotor. Core and winding are present in both the rotors. Outer frame or stator frame, it is the outer body, outermost part of the motor, which is visible to us. These are the cooling fins provided for efficient cooling. To these increase the area by which the heat dissipation is possible. And these are the feet. Through the feet provide the support to the stator frame and are fixed to the foundation with the help of bolts, foundation bolts. The stator supports the stator core. Here inside it is inserted stator core and keyed to the stator frame, and it also protect the other parts, that is rotor, etc., inside the motor from mechanical injury. The material used for rotor is material used for outer frame is generally cast iron or cast steel for small machines, but for large machines it is fabricated sheet steel. Cast iron is used owing to its higher mechanical strength, not due to the reason that it is a magnetic material, because magnetic flux is not conducted through the stator frame in case of three-phase motors. So we can make the stator from a non-magnetic material, for example glass, etc., if it possesses the required mechanical strength. Next is the stator core. Stator core is made of silicon steel lamination. One of the lamination is shown here. Silicon steel laminations. These laminations are insulated with the coating of varnish and are assembled together to this hollow cylindrical shape under hydraulic pressure. Axial slots are cut in the core, just like shown here, to house the stator windings. And these slots may be of three types: closed type, not open in the inner surface; semi-closed type, just like these shown in this stamping; and open type, depending upon the size of the machine. For large machines, these are open type; for medium machines, semi-closed type; for small machines, it may be closed type. The thickness of lamination is generally 0.3 to 0.5 mm. Because more the thickness of the lamination, more will be the eddy current losses. So to reduce the eddy current losses, the core is laminated. It is not made from the solid iron, rather it is made from laminations which are this much thick. And it also reduces the hysteresis loss, because silicon steel material have low retentivity. As a result, the hysteresis losses are reduced. Now let us discuss in brief what these eddy current loss and hysteresis losses are. When three-phase AC supply is connected to stator windings, a magnetic field is produced which is alternating in nature. Alternating field means the flux is changing always. The changing flux is linking with this iron core, and EMFs are induced in this core. Because it is having a closed circuit, so current starts flowing through this iron, which are not required in the motor action. These are called eddy currents. These currents are called eddy currents. These eddy currents produce a loss called eddy current loss, which is square of the eddy currents multiplied by the resistance of this path of the current. And what we do by laminating the core, we increase the resistance of the path of the eddy current. So area of cross section is reduced through which the currents pass. As a result, the current is reduced and hence the eddy current losses. So we should remember that core is laminated to reduce eddy current loss. Now, as we have already said that the magnetic flux produced in the core is alternating in nature, it faces the frequent reversals of flux. So if a material having high retentivity is used, then hysteresis losses will be much more. To reverse the direction of the magnetic field set up in one direction than another, there is a loss. So silicon steel have low retentivity, very low retentivity. It is a very good magnetic material, so that's why silicon steel is used. So laminated silicon steel reduces, due to laminations, eddy current loss is reduced. Due to use of silicon steel, hysteresis losses are reduced, and hence the motor functions more efficiently. Next is the stator windings. In the stator core, coils are placed which are wound for three phase. This diagram shows the stator windings, and three-phase AC supply is connected to these windings. Three-phase windings are placed in such a way that one-phase winding is placed 120 degree electrical apart from the other phase. Third phase is further at 120 degree, so total 360 degree is divided into three phases like this. But that angle is electrical degree. For two pole, electrical angle is equal to mechanical angle, and for more poles, more than two poles, electrical angle is mechanical angle multiplied by number of pair of poles. So if we have two pole, for example, if one end of the winding is in this slot, the other end will be approximately 180 degree from it. Approximately 180 degree. Like this coil will be bound. And if one winding R phase suppose is started here, then second phase Y phase coil will be started 120 degree after it, and B phase 240 degree after that. And this way three phase AC windings are placed in a stator core. These windings are made of enameled copper wire for having minimum copper losses, as copper has low resistance and enameling has the thin size insulation which is provided on this. In thin layer of insulation is provided, which is called enameling. Windings are placed 120 degree electrical apart that we have discussed. 6 terminals of three phase windings are taken out and are connected to the terminal block. From there off they may be connected in delta there, or through a starter they may be connected in star or delta as per requirement. These windings are wound for definite number of poles in a given motor. For example, for a 2-pole motor there will be one set of coils for each phase, and for a 4-pole motor there will be two sets of coils for each phase. That means the number of sets of coils is equal to number of pair of poles. The speed of the motor is inversely proportional to the number of poles. That is, more the number of poles, lesser will be the speed, and lesser are the number of poles, more will be the speed. So maximum speed will be obtained by having a 2-pole motor. Now here you can see how the coils are inserted in the slots. The coil inserted in one slot, this part of the coil is called coil side, another side is called coil side, and this portion which is seen outside the slots, that is conductors coming out of one slot and entering to the other slot, this part is called overhang or end connection. Overhang or end connection. This end connection does not participate in the functioning of the motor. Only the part in the stator core is the active part, which is called coil side. So as we have already discussed, the one phase coil, you can see here there are three sets of coil of yellow color in one slot, 2, 3, and other end goes at 180 degree electrical, and then next coil of the set, next slot, and second other phase, which is green here, it will start 120 degree from this point, 120 degree, and will be repeated in the same way as of the first phase. Then blue phase will start after 240 degree angle from the first. So like this, three ends, two end of phase 1, two end of phase 2, two end of phase 3 are taken out to the terminal block for connections of the motor to the supply. This diagram shows This is the coil which is inserted in the slots and its overhang is seen here. This part where there is a cut in the here, this is called slot. This area is slot, and between the two slots this part is called teeth. The teeth is this core part between two slots. This is called teeth. So this structure is like teeth slot, and so on. The slot opening may be different depending upon the type of slot. If it is open type, then this width of the slot is equal to opening. If it is semi-closed type, it is like this, that opening is small and inside the slot is large. For closed type, it will be closed here. The conductors will be inserted from one side and taken out from the other side. So this is about the stator windings. And now let us come to the rotor. First type of rotor is squirrel cage rotor. In this case of rotor, the core is made of silicon steel laminations. This is the core of the motor. In this case, slots are cut on the outer periphery. In stator core, the slots are cut on the inner periphery. Here, the slots are cut near the outer periphery. This is the slot opening. This line shows the slot opening. This line shows the slot core. So, core is made from steel laminations, not silicon, steel laminations. And in the slots are cut near the outer periphery. In the slots, these are the semi-closed type slots, conductors are inserted. In each slot there is a conductor. That conductor is a bar, solid bar, not the wire of small size. The bar size is equal to the size of slot almost. The slot bar conductors are inserted in the rotor slots which form the rotor winding, and those bar slots are short circuited at both ends by end rings. These are the end rings, short circuiting all the conductors, rotor conductors at both ends. These end rings are at both ends. This is shown the aluminium or copper end ring. If the winding bars of aluminium, then aluminium end ring is used. If copper conductors are inserted, then copper end ring is used to short circuit. This core is mounted on the shaft as shown here and is keyed to it. Now let us see why this motor is called squirrel cage motor and the rotor used in this is called squirrel cage rotor. If we take out the conductors of this rotor and end ring only outside and assemble it outside, this will be the shape. These are the end rings 1 and 2, and these are the conductors which are placed in rotor slots. So this is similar to the cage of a squirrel. That's why its name squirrel cage rotor. The rotor winding assembly is similar to the squirrel cage, so it is called squirrel cage rotor, squirrel cage type rotor, because the rotors are in that shape. Now the important thing of the rotor slots is that the rotor slots are not parallel to the shaft axis. They are inclined at some angle. You can see the straight line. If I draw parallel to this, it should come here. It should be like this, but it is inclined like this. So these slots are, this is called skewing of slots. The rotor slots are skewed. So why these slots are skewed? The skewing of slots gives some advantages to us. One is that it reduces humming noise and ensures the quiet operation of the motor. The noise level reduces. Second is we can obtain more smoother curves by using skewing slots for various positions of the rotor. and hence the motor vibrations are reduced. Next is the skewing of slot reduces magnetic locking between the stator and rotor core, due to which the motor may refuse to start at the time of starting. And due to the skewing of slots, the length of the rotor conductor also increases, which increases the rotor resistance because that is directly proportional to length, and this also gives the higher starting torque. Comparatively higher starting torque is achieved by skewing of slots. So skewing of slots gives these 5 advantages to us. It reduces humming and noise, smooth curves can be obtained, and it reduces magnetic locking between stator and rotor core, and increases rotor resistance, which results in higher starting torque. And let us come to the phase wound rotor. In phase wound rotor, or other name for this is slip ring rotor, core is similar to the stator core is similar to the squirrel cage rotor. Core is made of steel laminations, and slots are cut near the outer periphery of the rotor core, and these slots are semi-closed type again, and skewed again for the same reasons as discussed in the previous case. The only difference is that in spite of having solid bars inserted in the slots, here we have insulated windings just like the stator. Coils are wound first and then inserted into the coil slots for 3-phase, and windings are wound for same number of poles as that of the stator winding of the motor in which this rotor is to be used. One end, that is finishing end of the 3 phases, are connected in star, and starting ends are connected to slip rings. One phase here, second phase here, third phase to the third ring. Then these slip rings are insulated from the shaft. The rotor's core is also skewed to the shaft, so this whole unit rotates. Carbon brushes are pressed on the slip rings, by which we can short circuit these slip rings or add some 3-phase variable resistance or impedance to the rotor circuit. Through this we can also connect it to some external supply for some special purposes. In certain cases that is also used. So this is the difference of phase wound rotor construction from the slip ring. The main difference being the type of the windings used. Here we have coils wound for 3-phase, which are 120-degree electrical apart, and all the rules followed by the stator windings. The next part is miscellaneous parts, that is shaft. The purpose of the shaft is to transfer mechanical power to the load. The shaft is connected with the help of pulley to connect with it with load or some gear or some other arrangement whatsoever it may be. Shaft also supports the rotor and is supported by bearings, which are further supported by end rings. The shaft is made of mild steel and is having high torsional strength so that it should not break when load on the motor is applied. It supports the rotor parts. And then bearings. Bearings reduce friction between stationary and rotating members. Shaft is inserted in the bearing. The outer part of the bearing is supported and fitted with the end cover. And the bearings may be of 2 types, ball bearing or roller bearing. These reduces friction, and losses can further be reduced by properly lubricating the bearings with the help of grease, etc. The bearings are made of high carbon steel because they are continuously rubbing against each other, otherwise more wear and tear will be there if we use a soft material. It's a very hard and strong material. An end cover. End cover is made of cast iron or cast steel, or we can say it is made of same material as that of the stator frame. This part is the end cover, which covers it from end, and its purpose is to support the bearings through which our shafts are provided and rotating system is loaded on it, and it also protects the inner parts of the motor from mechanical injury as well as from dust and dirt, etc. So that's about the main parts of three-phase induction motor. Thank you.